Hi. So far we have been looking at simple harmonic motion, and we ended up seeing that if you have a mass spring system over here and you attached a certain mass to it, then we found that the net, and in this case we knew that the mass was going in either the positive x or negative x direction, right? So if you created an axis over here, you would have positive x, positive y, negative y. Okay? Now, basically, since then, we have seen that the net force acting on this mass is just given in terms of the Hooke's law, which is negative kx, and we know that the net force is just the mass times acceleration in the x direction, and that's because the displacement is only in the x direction, right? So that's why the acceleration is in the x direction as well. The acceleration in the y direction in this case will be 0 meter per second squared because the mass is not going up or down. So we don't care about the y direction, okay? Because the displacement only is in the x direction. Now, mass times acceleration in the x direction is negative kx. And we saw that in this case, we knew that the velocity is the displacement in x divided by displacement in time, so dx by dt. And we knew that the acceleration was the change in velocity by change in time, so that's dv by dt. So these are just these are notations for differentiation, and you will learn them in this month or so, right? And once you learn them, it won't look as complicated, okay? Just remember that differentiation is related to gradients, okay? You're just trying to find the gradient, which is why you're doing change in x by change in time. So it's related to finding the instantaneous gradients of a function, right? Now, if you look at the relationship, then you can basically say that, sort of like the acceleration is velocity by time and the velocity is displacement by time. So you can sort of bring them up together like this, right? So the point I'm getting to here is that you can say that the acceleration is d squared x by dt squared. So what this means is that if you take the derivative of the displacement, so if you do dx by dt, you get your velocity. And then if you do dv by dt, you get your acceleration. So from displacement, you get velocity. From velocity, you get acceleration. And then if you go this way, then it's like you're taking the double derivative of the displacement. Okay? Another way to think about it is that from x to velocity, you do d by dt. From velocity to acceleration, you do d by dt. So then from displacement to acceleration, you do d squared divided by dt squared. It's like you're taking the double derivative. Okay? And I explained this in one of the previous videos so basically you just need to know that in a displacement time graph, if you take the gradient, you get the velocity, right? So you would have learned this, that the gradient of a displacement time graph gives you velocity, and then the gradient of a velocity time graph gives you acceleration. And so that's where these differentiation notations come from, okay? It's related to differentiation and gradients. So yeah, so basically we were able to, we made this equation over here where we said that m times the d squared x by dt squared, right, plus kx is equal to 0. Okay? And we ended up getting to the point where we said that, you can't solve differential equations with the math right now. You would learn this in university, right? And so that's why, we just said that you had to accept the fact that there is this equation, acceleration is negative omega squared times x, right? And we also saw that in this case, the acceleration would be negative k by m times x. So then if you compare both of these equations, we said that omega squared is equal to k by m. Okay? So that's where we were so far when we were understanding simple harmonic motion. But here's actually an idea which I think would blow your mind away. So, let's say if you've got circular motion, right? So this is a circular motion. And let's say that we make this circular motion on an xy plane, okay? So this is the x-axis, negative x-axis, positive x-axis, positive y-axis, negative y-axis. And let's say we call this to be 0, 0, right? And now let's say that we create an arc. So let's say if this is a circle of radius a, and you have an angle theta over here. Okay, so that's what we have seen. That's what we have so far. Okay, now the main idea for this is that, let's say that if you have this, let's say if this is an object, right? So some sort of circle, and then you're just going in circular motion like this. Okay, so one thing you need to know is that if you go in this direction, you're going in the direction of positive theta, and then if you go in this direction, you're going in the direction of negative theta. Okay, so we will say that the pendulum, or in this case the circular mass, is going in the positive x direction. So this is how the direction would be going. Okay, so this is our object performing circular motion. Okay, now the main idea I'm trying to explain is that simple harmonic motion is just circular motion in one dimension. So circular motion happens in two dimensions, but simple harmonic motion, you just do it in one dimension, and that's it. So let's take this as let's just make this as 1D, right? Okay, so if you think about it, over here, this pendulum is first going from, so this is, as we know, let's call this positive A, and then let's say this is negative A, and let's say that this 0, 0 is the equilibrium. Okay, so positive A is like the positive amplitude, so that's the maximum displacement from the mean position, and negative A is the negative amplitude, and 0, 0 is the equilibrium. Okay, now if this object is going in circular motion, so first it starts off with the positive amplitude and it goes to the negative amplitude. So if we write it over here, then it's like it's starting at this positive A and then it's going to negative A. Okay, so this is positive A, it's going to negative A. Now once it's over here, let's say if it goes from negative A back to positive A, right? So this is performing circular motion, as we can see in two dimensions. And if we just look at the x displacement, it's like it's going left to right, right to left, left to right, right to left. Okay, so this is one cycle. So if this is one cycle, it goes to the left, right? And then if this is another cycle, then it goes back to the right. So it's oscillating in this left and right direction. And if you think about it, that's exactly how a mass spring system works. So you've got a mass spring system, you have attached a mass to it, then even this mass oscillates between a certain amplitude, right? So if this is negative amplitude, positive amplitude, then this mass also oscillates in the left and right direction. Okay, so therefore simple harmonic motion is just circular motion in one dimension in a way. So you can think of the similarity between the two. And I think this makes it a lot more easier because, in IB physics, they put simple harmonic motion with waves. And I think psychologically, when people think of waves, they think it's going to be hard. Whereas circular motion, people tend to think it's a little bit better, right? So yeah, simple harmonic motion is just circular motion in one dimension. And so what we can do is that we can just derive all of the very important equations we have learned. So, let's say that if this is a circle with radius A, and I make this right angle triangle, and then this is 90 degrees, okay? So we know that this x displacement over here, we know that this x value is A cosine of theta, right? And then we know that this y value is a sine of theta, correct? Okay, so that's basically trigonometry that we're applying over here. And just if you see, the radius A is just the amplitude, so the magnitude of the radius is the same as the amplitude. So as you can see, if this is 0, 0 and this is 0, 0, then if you go to the right, you get to the positive amplitude as you get over here. Okay, so that's why we can say that the instantaneous x displacement is A cosine of theta. And the very interesting part over here is that we know that the angular velocity omega is the change in theta by change in time. And so we can say that the change in theta is equal to omega times t. Okay, so we can say this. So if you find the instantaneous x displacement, then x is just a cosine of theta, which is a cosine of omega t, right? Now, if you would have seen this equation in HL, then your teacher would have perhaps told you that the x displacement in simple harmonic motion is x naught cosine of omega t. Okay, so in SL, you don't really need to know these specific equations, but it's good exposure. So it's sort of like the instantaneous x displacement is just this cosine function. Okay, and then if you find the velocity function, you just do a simple differentiation. So the derivative of x naught cosine of omega naught t is negative omega naught x naught sine of omega t. And then the acceleration, you do the derivative once again. So this is negative omega naught squared x naught cosine of omega naught times t. Okay? And if you see, we get this famous equation where we know that the acceleration is negative omega naught squared. Then this is x naught, and then this is cosine of omega naught t. And then we can just call this to be x. So we saw that this x is just a cosine of omega t, right? And we just call a as x naught. So the reason we call this as x naught is because x naught is the amplitude. So we just substituted a with x naught. Okay? And so, we get this familiar equation that a is negative omega squared x, which is precisely what we got over here. Okay? So, therefore, as you can see, we were able to derive the simple harmonic motion we were able to derive the equations by just observing circular motion, right? Now, if you see in circular motion, you have two dimensions. You have the y value, which is a sine of theta, and then you have the x value, which is a cosine of theta. But we discard the y dimension because we only care about one dimension, so that's why we take it to be that's why we would take it to be a cosine of theta. Okay, so that's the main idea where x is equal to where we were able to derive these equations, right? Okay, so now right, so and another thing we can look at this in terms of the simple harmonic motion and circular motion is this very interesting example. So let's say if I make the circular graph over here, right? So this is circular motion, and then once again I make this to be positive x, negative x, and then this one can be positive y and negative y, right? And if you would think about it, then in this case, if you see this carefully, then we can say that, let's say if you have an object performing circular motion in this case, right? And let's say that this is the center of the circle 0, 0. So we can draw the instantaneous velocity vectors. So we know that the instantaneous velocity v is going to be tangential to the path of movement. Okay? So this is going to be velocity v. It's going to be tangential to the path of the movement. So we're just making tangents over here. Okay? Now we know that for each of these, the velocity and the centripetal acceleration will be perpendicular. So the centripetal acceleration will be acting towards the center of the circle. Okay? Or the centripetal force will be acting towards the center of the circle. As we can see over here, centripetal forces are acting to the center. Okay? Now, the main idea you can note over here is that in this case, the centripetal acceleration A centripetal is given by v squared by r, right? And we also know that in this case, we know that the velocity is equal to 2 pi r by t. Okay? So the reason it's 2 pi r by t is because 2 pi r is just the circumference of the circle. So because it's the circumference of the circle, then velocity is displacement by time, which is 2 pi r by t. Okay? And we know over here that omega, which is our angular velocity, is change in theta by change in time, which in this case can be of the form 2 pi by t, where t is the time period and 2 pi is the overall angular displacement, right? So in a circle, the maximum angular displacement you can make is 360 degrees. And in this case, this is like one oscillation, so you can do it in one entire time period, capital T. Okay? So that therefore we derive this formula over here that the velocity is, so 2 pi by t can be written as omega, so v is omega r. So we just substitute it back here, and we see that in circular motion, a centripetal is omega r squared by r, which is omega squared r. And if you look back at what we got over here, then we got that acceleration is negative omega squared x. So you can sort of think of r as a displacement for x. Okay? So you can think of it in terms of that. So it's not a coincidence that we're getting a equation of a similar form, right? Okay. Now, the main idea over here is, so this is also another important idea. So you would have seen that the acceleration is negative omega squared x, right? So you might be wondering where this negative sign is coming from, because in our centripetal acceleration one, we got that acceleration is omega squared r. But over here we're getting positive. So you might be thinking how we might be getting negative. And the answer for that is a bit unclear, I would say. Although this is how I would sort of think about it, right? I can't say for 100% if this is the official answer, but this is how I would reason with it. So my reasoning for this is that, let's say that if the velocity is going in the, in this case, the tangential velocity and the displacement, which is tangential, so this displacement is going in the positive y direction, right? And in this case, what we can see is that the centripetal acceleration, right? So the centripetal acceleration, a centripetal, is going in the negative x direction, okay? Right? So, let's see. The main thing is sort of like, you can sort of you can relate that sometimes when our displacement is positive, then the centripetal acceleration is negative, right? But sometimes in these cases, we can see that our displacement is in the negative x direction and the centripetal acceleration is also acting downwards. Okay? So in this case, the centripetal acceleration is negative, but the displacement is also negative. So I would just say that there are some points in the circular motion over here. So some points during the circular motion, we see that the centripetal acceleration is acting to the right, whereas the displacement is acting downwards. So sometimes when centripetal acceleration is positive, the displacement x is negative. So it does not happen at all 4 points, I would say. But like for example over here, if the object is going to the right, then the centripetal acceleration is acting upwards. So if x is positive, centripetal acceleration is also positive, right? So yeah, so that would just it's sort of like it can be one reason why you have a negative sign, right? That could be one of the reasons over here. Like if you wanted to think about it in a brute force way, I would say, then you can make this 0, 0, and you can reason that, let's say that if the displacement is going upwards, so if the displacement is going upwards, then we know that the centripetal acceleration is acting towards the center of the circle, and the displacement is just the tangent at the point. And then in this case, we can see that if the centripetal acceleration is going to the left, then the displacement is going downwards, right? Okay, so this is how things are happening, right? So that's how you could reason it, that at some points in the circle, or actually, yeah, so in this case, as we can see, at these two specific points, so these 2 points are located on the x-axis, right? And we only care about the x-axis, okay? We only care about relationships at the x-axis, because we know that simple harmonic motion, SHM, is just circular motion in 1D, right? That's what it is. So the other way we can think about it is that we don't care about these 2 points. So, we don't care about these 2 points where the centripetal acceleration is acting up and the displacement is to the right and over here. So we don't care about these 2 points since, they're not physically on the x-axis. So we can say that whenever you have a relationship on the x-axis, you can see that on the positive amplitude, so this is positive amplitude, this is negative amplitude, we can see that on the positive amplitude, where when x is positive, centripetal acceleration is negative, and then on the negative amplitude, when the acceleration is positive, the x displacement, which is over here, is negative. So therefore, you can sort of say that when we got the centripetal acceleration is omega squared x, then you put a negative sign to symbolize the relation. Okay? Right. So the main idea for the video is that we were able to sort of prove the similarity of how simple harmonic motion is just circular motion in 1D. And we were able to derive the displacement formula, right? So we were able to get that x is a cosine of theta, and we know that theta is omega times t, as we saw. So this is a cosine of omega t, and we just said a is x naught. So x naught is just another symbol, cosine of omega t, right? And you can find the velocity and acceleration by just doing differentiation. Okay, so it's a very simple differentiation. You'll learn it if you haven't learned it yet, right? And yeah, so if you would see, these are exactly the equations we got for SHM. So these are exact equations for SHM, right? So this is a very simplistic way of deriving it, right? Rather than going the other complicated way about it, right? And then the last thing, which we ended up getting, is that the centripetal acceleration is omega square r, but we saw that if we only care about the x dimension, then in the x dimension, what we saw is that, if we saw it in the x dimension, then we saw that over here, if x is positive, acceleration is negative, and then in this x dimension, if x is negative, so if the object is going in the negative y direction, then acceleration is positive because it's acting in the positive x direction. So we could sort of make this negative sign relationship between these 2 things when we are looking at the x-axis. Okay? Alright, so that's how we look at SHM. Main thing is, don't think of this as a topic in waves. It's not really closely related to waves. It's more of like circular motion, lots of trigonometry. You need to be very strong in trigonometry. So circular motion, trigonometry, and then some basic differentiation. So just basic differentiation. Okay? All right. Okay, good luck. All right, good luck.